Chapter 19, the hydrogen atom and the hydrogenic ions. Section 19.3, the properties of the hydrogen atom. Given the wave functions of the electron in the hydrogen atom, we can determine its physical properties. For example, we can apply the Hamiltonian operator to the wave functions to get the corresponding eigenvalues. Those eigenvalues are the energy of the electron. The 1s orbital has a wave function of e to the power of negative r multiplied by a constant. Now we can apply the kinetic energy operator to the wave function and also the potential energy operator negative 1 over r to the same wave function. And now we can just do mathematical derivations, because in this wave function we do not see theta or phi. Therefore, the first derivative of this wave function with respect to theta is 0. The second derivative with respect to phi is also 0. We have only this term here applied to this function. That's why we can simplify the left-hand side dramatically. And also we have the potential energy operator applied to psi. Now let's evaluate this. We do see n as a constant, the normalization constant. We can take it out. And the first derivative of e to the power of negative r is negative e to the power of negative r. Two negatives cancel, so we have this equation over here with this negative and another negative from here cancel. Now we just need to take the derivative of r squared times e to the power of negative r. And over here again, this is just the potential energy operator applied to the wave function. We expand this using the product rule. It's 2r times e to the power of negative r, and then minus r squared times e to the power of negative r. And we can simplify this expression. In the end, we get 1/2 times this wave function with a negative sign in the front. What does that mean? That means, well, first, this is indeed an eigenfunction of the Hamiltonian for the hydrogen atom. And number two, the corresponding eigenvalue is negative 1/2. And this is in atomic unit. One atomic unit is roughly 4.36 times 10 to the power of negative 18 joules. Again, this n is the normalization factor, so you can see in my derivation I did not even use the value of n, so we get this result regardless of n. This is because the Hamiltonian is a linear operator, so even if you change the value of n, you're not going to change the eigenvalue. The eigenvalue of the 1s orbital wave function is negative 1/2 atomic unit of energy. That means, well, if the electron is in the 1s orbital, it has an energy of negative 1/2 in atomic units. And also it means, well, the total energy in the 1s electron is negative 1/2. We have this expression here. Now let's look at the 2pz atomic orbital energy as another example. The wave function says it's the normalization function over here times r times cosine theta times e to the power of negative r over 2. Over here, when you have a principal quantum number 2 here, you see this principal quantum number here on the bottom. So it's negative r over the principal quantum number. R times cosine theta is really c, but it's more convenient to use r theta and phi here. Again, n is the normalization factor, so it does not really affect the eigenvalue we will get in the end. We apply this Hamiltonian to the 2pz wave function. So over here we have the kinetic energy operator, and over here potential energy operator being applied to the wave function. Now if you look at the wave function, it does not depend on phi at all, so this term disappears. We have only two terms in this kinetic energy operator. This is just the potential energy operator, negative 1 over r, applied to the wave function. Now we need to apply this operator to the wave function and this operator to the wave function. We do that separately. So over here, well, we just need to use some calculus skills to get this derivative, which is here. Again, you need to use the product rule. We get something here. Over here it's easier because look, this r terms does not depend on theta, so we can take all those r terms out. We're just gonna take the first derivative of cosine theta and then times sine theta over here, and then whatever the result is, we take its first derivative and then divided by sine theta. So that's why we got this expression over here. And this part is just from the potential energy operator applied to psi. R and R cancel, so we have this. Again, calculus and algebra. So we get this over here. The first derivative of cosine theta is negative sine theta, so we get this. And we keep doing those mathematical operations. It's purely mathematics. All the way to here, it looks really tedious. And this part goes here, this part goes here. But if you look at all those terms, they have a common factor. Well, the common factor is this. Pay attention here. We have n cosine theta, n cosine theta, n cosine theta. So we see this everywhere. We have this n cosine theta. And then we include every other, terms over here just inside. So this goes here, this goes, this two together goes here, because this two can be combined. So this two together goes here, and this term goes here, this term goes here. Finally, the potential energy applied to the wave function goes here. So we can clean it up. I think this two will cancel, this two will cancel. In the end, we get negative 1 over 8 nr cosine theta e to the power of negative r over 2. It happens to be negative 1 over 8 multiplied by the wave function of the 2pz orbital. So we proved two things. One is indeed this is a eigenfunction of the Hamiltonian for the hydrogen atom. Alright, so this function is an eigenfunction of the Hamiltonian for the hydrogen atom. And number two, the eigenvalue is negative 1 over 8. That means the energy of the electron is negative 1 over 8 in atomic units. And one atomic unit is 4.36 times 10 to the power of negative 18 joule. It's just a constant. Well, over here we're looking at the wave function for the 2pz orbital in the hydrogen atom again. We apply the Hamiltonian to the wave function. We get negative 1/8 times the wave function. So again, the physical meaning is pretty simple. The eigenvalue is negative 1 over 8. Therefore, the atomic orbital energy is negative 1 over 8. The total energy of the electron in the 2pz orbital is negative 1 over 8. And in general, without proving everything, the energy of the electron in the hydrogen atom is negative 1 over 2n squared in atomic units. N is the principal quantum number. So if you have n equals 1, it's negative 1/2. When n is 2, negative 1 over 8. N equals 3, like a 3D electron in the hydrogen atom, well, it's going to be negative 1 over 18. What if you promote the electron to the 4f orbital? The energy is negative 1 over 32. When the electron makes transition from one level to another level, we can compute the energy change. Well, the equation is this. If an electron jumps from the mth level to the nth level, well, we have this equation, and this is the energy change. Now we're going to set an equation over here. We're going to set this. Well, hc times over here, this is the Rydberg constant, times 1 over m squared minus 1 over n squared. Well, this is the energy difference between the transition from level m and level n. When we learned this Rydberg equation in general chemistry. And over here we have the energy difference between the mth energy level and the nth energy level in quantum chemistry. So we can put equal sign in between to determine the value of the Rydberg constant. So you can see h times c times the Rydberg constant is 1/2 atomic unit. 1/2 atomic unit is this much in joule, and the Rydberg constant is 1/2 atomic unit of energy over h over c. We get this value, well, 1.1 times 10 to the power of 7 per meter, and that's indeed the value of the Rydberg constant. Well, now of the wave functions of the hydrogen in the of the electron in the hydrogen atom is an eigenfunction of the potential energy operator. That means we will never know the exact potential energy of the electron in the hydrogen atom. However, we can evaluate the expectation value of the potential energy using quantum mechanical postulate 4. For example, let's look at the 1s electron in the hydrogen atom. We just need to use postulate 4 and this is the expectation value of the potential energy, -1 over r. Why -1? Well, it's just negative E squared. E is the charge of the electron, only because the charge of the proton and the charge of the electron have opposite signs. So now we have this postulate 4 being used here with two integrals, one on top, on the bottom. On the bottom, you have psi star times psi. On the top, you have psi star multiplied by, well, the operator applied to psi here first. You need to do this operation first and then multiplication. So over here, I'm just writing out the integrals. I'm using the volume element in the polar spherical coordinates, which is r squared sine theta dr d theta d phi. Again, this is the volume element of a three-dimensional space in the polar spherical coordinates. Alright, and I think I see this n on top twice and on the bottom twice. So the normalization factor will eventually cancel, n squared and n squared will cancel. And there's a trick of evaluating a triple integral. That is, if you can separate the variables, do that. So what I'm going to do is I'm going to just separate the variables. Over here we have an integral of r, and over here, sorry about this, I think there's a typo here. I need to quickly fix the typo here. There's no dr in here. Alright, now we're good because we're evaluating the function of r over here. And again, on top you have a triple integral. I'm just separating this to a single integral of r over here on top, and this is on the bottom. Because of this -1 over r, we have a negative sign here, and because this -1 over r is multiplied by r squared, so you have r here, and on the bottom you have r squared here. If you look at theta and phi, well, on top you have a double integral of theta and phi. On the bottom you have the same double integral of theta and phi, so they will eventually cancel, and then we get this simplified expression for the average potential energy. Sometimes we just use Wolfram alpha to get those values. Make sure you know r is from 0 to infinity, but we can also derive this by hand, this general equation by hand, and then use this equation to get the value of the top integral, which is 1 factorial over 2 to the power 2, and the bottom integral is 2 factorial over 2 to the power 3. The result is -1. So we can, again, we can prove this by hand, but I'm gonna skip this part. We'll just use this expression and plug in the values of n in the expressions here. We get -1, and when you see -1, it's actually -1 atomic unit of energy, and that's actually -4.36 times 10 to the power of -18 joule. The expectation value of the kinetic energy is going to be the total energy minus the expectation value of potential energy. So it's -1/2 minus -1. We get +1/2 atomic units. So it's just simple. It's just because the total energy is the sum of its kinetic energy and potential energy. So if you are interested in the average kinetic energy, we can always get the total energy and also the average potential energy. Take the difference, you get the average kinetic energy. Now let's look at the expectation value for the potential energy of this 2pz orbital. We're going to use quantum mechanical postulate 4 again. We have the complex conjugate over here. This is potential energy operator applied to the wave function. On the bottom, it's the integral of psi star times psi. So we're plugging all those integrals, and you'll see we can separate this triple integral on top into 3 single integrals. One of r, one of theta, one of phi. And same here on the bottom. But you probably notice that the angular part on top and the angular part on the bottom are exactly the same. So on top, the integrals of theta and phi and the integrals on the bottom of theta and phi, they completely cancel. So I'm not going to show you the detailed derivation, but you can see over here we need to integrate cosine theta, sine theta, d theta. On the bottom, cosine theta, I'm sorry, I forgot this cosine theta. So on top, we need to integrate cosine theta times cosine theta times sine theta d theta. On the bottom, we need to integrate cosine theta, sine theta, d theta. They will cancel. And again, on top, we need to integrate this d phi. On the bottom, we'll just integrate this d phi, so they also cancel. That's why you can see there's only the integrals of a function of r on top and also the integral of a function of r on the bottom. Look, you have r to the power 3 on top, r to the power 4 on the bottom. Well, only because on top we have this 1 over r operator. The negative sign goes here, so and then we can just evaluate this. How do I evaluate this? One way is to use Wolfram Alpha, but also you can actually hand derive this. It's possible to just derive this and plug in the values, and then we have -3 factorial over 4 factorial. We'll get -1 over 4. That's the average potential energy of the 2pz electron in the hydrogen atom. The unit is atomic unit. Again, this n is the normalization factor. You can see n appears on top 2 times and also on the bottom 2 times. They cancel. The expectation value of the kinetic energy is, well, the total energy minus the potential energy. We get a positive 1/8 atomic unit of energy. Well, it is counterintuitive, but the higher energy 2pz electron in the hydrogen atom moves slower than the 1s electron. Alright, so it's kind of strange, but it's true. If you have 2pz electron, its kinetic energy is only 1/8. The kinetic energy of 1s electron is actually 1/2 atomic unit. In general, the total energy of the electron in the hydrogen atom is always -1 over 2n squared atomic unit. The expectation value of the potential energy is -1 over n squared, so this is 2 times the total energy. The expectation value of the kinetic energy is 1 over 2n squared, and n is the principal quantum number. So you can see the kinetic energy and the total energy have the same magnitude, but different signs. The total energy is negative, the kinetic energy is positive. The magnitude is 1 over 2n squared. Given the angular part of the wave function of electron in the hydrogen atom, we can also determine its average rotational energy. If somehow we can determine the expectation value of 1 over r squared, because the rotational energy is just L times L plus 1 times h bar squared over 2I. I is the moment of inertia. We can determine the exact angular momentum in the 3-dimensional space. It's the square root of L times L plus 1 and then times h bar, and also its z component, which is just m sub L h bar. So how do we know this? Well, again, we can just apply the corresponding operators, to the wave function to get those. For the s orbital, L is 0. Therefore, the magnitude of the 3-dimensional angular momentum is the square root of 0 times 1 and then times h bar, which is 0. M sub L is 0. Therefore, this is just 0. If you have a p orbital, L is 1. Therefore, the magnitude of the 3-dimensional angular momentum is square root of 2 times h bar. What about the z component? We may have 3 different values. It can be 0. It can be plus minus h bar when m sub L is plus minus 1. Again, px and py, they do not really have a specific value for the z component. We need to do a linear combination of px and py to get either plus h bar or negative h bar. So again, p plus minus 1 wave functions are linear combinations of px and py. At the same time, px and py are linear combinations of p sub plus minus 1. When we have a d orbital, well, L is 2. The 3-dimensional angular momentum is just square root of 6 h bar. The z component can be 0 plus minus 1 plus minus 2 h bar. What if we have L equals 3 for f orbitals? Well, the square root of 3 times 4, that's the square root of 12. We have square root of 12 h bar. The z component can be 0, plus minus 1, plus minus 2, plus minus 3 h bar. We have a degeneracy of 7 here. When we have a g orbital, L is 4. The 3D angular momentum is the square root of 20 times h bar. The z component can be 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4 times h bar. Well, now the wave functions of the electron in the hydrogen atom is an eigenfunction of the radius operator. So we will never know the exact radius of the electron in the hydrogen atom. We can, however, evaluate the expectation value of R, the radius. Same thing possibly for the complex conjugate of the wave function, and then the operator applied to the wave function on top. On the bottom is just the integral of complex conjugate times the wave function. We plug in all those expressions for the wave function, for its complex conjugate, and plug in the operator here. When we apply the R operator to a function, it's equivalent to the multiplication by R, and then we have these two integrals. How do we evaluate this? Again, we're going to use this expression over here, and we plug in a equals 3 versus a equals 2. Over here, we have 3 factorial over 2 to the power of 4, and on the bottom we have 2 factorial over 2 to the power of 3. We get 1.5. So the average radius is 1.5 for the 1s electron. Alright, so that's the physical meaning of this. We can also get the average for R squared. It's just we need to use R squared operator instead of the R operator. So on top, this is R cubed, this is R to the power of 4. So that's the difference. We evaluate these two integrals. We get the average for R squared, which is 3. And now we can even determine the standard deviation. It's just the square root of 3 minus 1.5 squared. We have the standard deviation for the radius of the 1s electron in the hydrogen atom. And this standard deviation is very large compared to the average value. The average is 1.5. And the standard deviation is about 0.9 atomic unit of length already. Remember, 1 atomic unit length is about 0.529 angstrom. We can also look at the most probable radius of the electron in the hydrogen atom. So the probable radius can be determined by maximizing this R squared. This is the radial function. Y times R squared, well, it comes from the volume element. The volume element is R squared times sine theta dr d theta d phi. So we need to maximize this whole thing. So when we set its first derivative to 0, we can expand it using the product rule in calculus. We get this equation. And the lowercase r cannot be 0, the uppercase r cannot be 0. So therefore, we have only one legitimate solution. This radial function is equal to negative r times its first derivative. So we're going to just solve this equation for different wave functions, well, to get the most probable radius, which maximize this over here. This is the probability density as a function of r. So now let's look at the 1s orbital. When you have 1s orbital, the radial function is e to the power of negative r. Again, don't worry about the normalization factor. It does not play a role here. So we're going to just write out this equation. We take its first derivative. We plug it in here. We solve this equation. R is 1. So the most probable radius of the 1s electron is 1 atomic unit of length. It's actually smaller than the average average radius, which is 1.5. The root mean squared radius is 1.732 atomic unit. So in general, the most probable radius is smaller than the average radius. The average radius is always smaller than the root mean squared radius. And when the principal quantum number n is larger, well, all those three radii, the most probable radius, the average radius, and the root mean squared radius are all larger. The electron is further away from the nucleus. when the principal quantum number is larger. Again, we can just calculate the most probable radius given the wave function. Now let's look at the 2s wave function. We have this polynomial function. Well, it's the first order multiplied by exponential function over here. This is the function of r for the 2s electron. Again, we use this equation, r plus the lowercase r times the first derivative of the function of r is 0. We plug in the expression here. This is the function itself, and this is the first derivative. We have a common factor, e to the power of negative r over 2. So both sides divided by this exponential function, we get this. And then from here, we get a second order equation or quadratic equation. Solving this, we get two roots. Both are legitimate roots. That means if you have a 2s electron, there should be two maxima, one at 3 plus the square root of 5, one at 3 minus the square root of 5. So the numerical values are 0.764 atomic unit and 5.236 atomic unit. Again, there are two maxima in the 2s orbital. And between these two maxima, there's a node, there's a spherical node. I think we determined this spherical node before. When r equals 2, we have a spherical node. Oh, by the way, if you just set this to 0, r is equal to 2 to have this spherical node. So that's pretty easy. Now let's look at a 2p wave function over here. Again, we use this equation. It's just r plus the lowercase r, the radius, times the first derivative of the function. This should be 0. We solve this equation, r equals 4. So if you have a 2p electron, there's only one maximum. That maximum is at 4 atomic unit of length. And for the 2p electron, there's no spherical node. There's only one planar node. Now let's look at this radial distribution of various wave functions of the electron in the hydrogen atom. The most probable radius of the 1s electron is 1 atomic unit. So right here you can see it's 1. For the 2s electron, there are two maximum. Let's look at the 2s, the shape here. You have a bump here, another bump here. They are just two maximum. Over here, this is 0.764 over here, a bit less than 1. And then another one is 5.236, a bit above 5. So you can see this is a bit above 5, right? For the 2p orbital, we learned that the most probable radius should be the maximum or the most probable radius is 4. So you can see over here, this is maximum of the probability density. It's just 4 atomic units. So again, given the wave function, we can easily calculate the most probable radius. And I showed you how to calculate the average radius, the root mean squared radius, the standard deviation of the radius. At least we know we cannot determine the radius of the electron exactly. However, we can have the distribution, and you can see this distribution for the 1s electron, the distribution for the 2s electron with two maxima separated by a node, a spherical node. We can see this 2p distribution, only one maximum without any spherical node, and you can see 3D, the wider distribution, all right, and a larger most probable radius. I think this is about 9 over here. 3p has one spherical node separating two maxima, and then 3s has three maxima, 1, 2, 3 maxima separated by two spherical nodes.